with this video, I was debating if to show it or not, just because there's some complex things in here that we won't touch on. But then, with but then I decided it's good to just visualize what we're about to be talking about. So I'm showing it. So take as much in as you can, and then try to remember some things. I'll quiz you at the end.
I'm not good at that quiz stuff, but I'll try.
It's all right. Give her a shot.
I'll give it a shot.
It's 12 minutes, or 9 minutes, excuse me.
Humans, like chemicals, are really all about bonds. Think about all the relationships in your life. You're a casual acquaintance to some people, a colleague or friend to others, and maybe more to that someone special. Maybe casually, if you're in a committed relationship or you're married, there are all kinds of different combinations of people out there. And sometimes, people fall for a vampire or a werewolf. Who am I to judge? Fact is, each type of relationship requires different things from you and the other person. But if you play your cards right, these relationships allow you to relax and escape the stresses that come with the constant search for affection. Distance is important in relationships too. Of course, too much distance makes it hard to stay focused on each other and requires a lot of effort to keep things together. And I may not have to tell you, too little distance can be a problem as well. Everyone needs their space, and when you don't have any, you just end up pushing away from whatever's crowding. In this way, atoms are a lot like us. We call their relationships bonds, just like we do with our own relationships. And there are many different types. Each kind of atomic relationship requires a different type of energy, but they all do best when they settle into the lowest stress situation possible. The nature of the bond between atoms is related to the distance between them, and like people and vampires and werewolves, I suppose, it also depends on how positive or negative they are. The difference is that, unlike human relationships, we can analyze exactly what makes different kinds of chemical relationships work, and that's what this episode is all about. But people, please remember that we here at Crash Course do not dispense relationship advice. First things first, why do atoms do this at all? Well, like everything else in the universe, atoms do whatever they can to reduce their overall energy. And they reach their lowest energy by achieving a balance between attractive and repulsive forces, being neither too clingy nor too aloof. So when two atoms approach each other, the electrons of each are attracted to the protons of the other. This is the electrostatic force. Like charges repel, opposites attract. Like in real life, or at least Paula Abdul songs. I know, I'm old. So when one atom is attracted to another, just like Edward Cullen and Bella in chemistry class, to use a slightly more timely reference, it ggets stressed out by the attractive force and tries to relieve the stress by getting closer. We've all been there, right? That hot, nerdy vampire girl in your chemistry class, it's intense. The pull is so strong that the stress level or energy rises when the two are separated, so they stay close. But sometimes they can get a little too close. When that happens, the nuclei repel each other because of their like charges, and the energy between them rapidly increases, and they both back off just enough to find that perfect little distance between them, and everyone relaxes. This ideal, wonderful distance is the bond length. It's the distance between two nuclei at the point of minimum energy. In other words, where the attractive and repulsive forces cancel each other out. The distance at which these two atoms of chlorine reach their minimum energy, caught between the attraction of the electrons to the nucleus and the protons repelling the nuclei, is the bond length. That energy minimum, which we know absolutely is negative 239 kilojoules per mole, occurs when the distance between the atoms is 0.00199 nanometers. That distance is the bond length of Cl2, chlorine gas. Now, because the electrons are attracted to both nuclei in the molecule, they actually spend the majority of their time in the space between them. This is often described as sharing electrons, and we call this kind of bond a covalent bond. But not all sharing is equal. As you know, I have an older brother. The strength with which an atom holds shared electrons is called its electronegativity. The electronegativity of various elements are all super well known and waiting for you in tables on the internet. If two atoms in a bond have very different electronegativities, like say hydrogen at 2.1 and oxygen at 3.5, the electrons are more attracted to the atom with the higher electronegativity. The difference is so great that the electrons spend most of their time around the stronger atom and much less time around the other one. Like how all of the neighborhood kids wanted to hang out with John, my older brother, because he was more charismatic. When the electrons hang out closer to one side of the bond, it creates a slight negative charge in that area and a slight positive charge around the other atom. This separation of charges is called polarity. And it's the polarity of the molecule that these atoms form, H2O, that makes water the most important molecule on Earth. Covalent bonds like this, where electrons are attracted to one atom more than the other, causing a separation of charges, are called polar covalent bonds. But when a covalent bond forms between two identical atoms, like the two chlorine atoms in our graph earlier, the electrons are distributed evenly. We call this a nonpolar covalent bond. But you've also got to consider the middle option, where the atoms aren't identical but have very similar electronegativities, like hydrogen with an electronegativity of 2.1 and sulfur at 2.5. The difference here is so tiny that the electrons are pretty much still evenly distributed, and we call that a nonpolar covalent bond as well. There's a huge world of important chemicals that have these kinds of bonds, so many in fact that we will dedicate a couple of separate episodes to them. Covalent bonds tend to form from nonmetals and sometimes metalloids, those elements that have both metallic and non-metallic characteristics. That's because most of them hold their electrons so tightly that they're more likely to share them with another atom than to gain or lose them altogether. Metals, on the other hand, have loosely held outer electron shells, so they're constantly dropping electrons and becoming positive ions. And when positive ions come across negative ions, like those formed from halogens, for instance, you have to know what's going to happen. They're attracted to each other, which means energy is required to keep them apart, which means that they're gonna bond if they can, creating that oh-so-wonderful point of minimum energy. This type of bond is unsurprisingly called an ionic bond, a bond formed between a positive ion and a negative ion. Because the ions are formed when one atom loses electrons and the other gains them, we often say that an ionic bond is formed by the transfer of electrons from one atom to another. And we can calculate the amount of energy that exists in a bond between ions at a given distance using a formula called Coulomb's law. Note that this only works for ionic bonds because the calculation requires the charges of the ions, which covalent bonds don't have. Coulomb's law says that the energy between two ions equals the product of the two charges, which are represented by capital Q's, because why not, divided by the distance or radius between the two nuclei, all multiplied by a constant. 2.31 times 10 to the negative 19th joules per nanometer. Of course, the radius also has to be expressed in nanometers. You gotta make the units match. Let's see how it works with something simple, sodium chloride or table salt. We know that the normal charge on sodium ion is +1 and the normal charge on chloride is -1. These are Q1 and Q2. The length of a stable NaCl bond is 0.276 nanometers, so we put that in for the radius. And finally, a quick calculation tells us that the bond contains -8.37 times 10 to the negative 19th joules of energy. Remember that negative number represents a decrease in the energy of the system due to an attractive force, which certainly makes sense here. Sodium and chloride ions are strongly attracted to each other due to their opposite charges. Of course, you might have noticed that -8.37 times 10 to the negative 19th joules looks like a tiny, tiny number, but keep in mind we're talking about one single pair of ions. The negative 239 kilojoules that we got for chlorine, that was for a whole mole of molecules. When multiplied by the 10 to the 17th or so ions in a single grain of table salt, and then by the thousands of grains of salt in a mole, the energy becomes much more significant. The NaCl bond is in fact quite strong. And because they consist of a positive ion and a negative ion, two charges completely separated between two different particles, ionic bonds are extremely polar. Way more polar than polar covalent bonds. And so those are our three types of bonds. Nonpolar covalent, formed by the equal or nearly equal sharing of two electrons between nonmetal or metalloid atoms. Polar covalent, formed by the uneven sharing of electrons between two nonmetals or metalloids. And ionic, formed by the transfer of electrons from a metal to a nonmetal. It's important to remember, though, that there aren't only three designations for chemical bonds. Just like human relationships, bonds don't always have really well-defined boundaries. Everything is a continuum. Labels are useful, but they can only take us so far. There are, however, certain properties that each kind of bond tends to have that you should know. For instance, ionic compounds are often crystalline in their solid form because of the way the ions pack together, like salt is. They're generally soluble in water because the two ions interact separately with the positively and negatively charged areas on a water molecule. And once they're separated or dissolved, the ions allow the solution to conduct electricity. Covalent compounds, on the other hand, tend to be softer solids, liquids, or gases like Cl2 is at room temperature. They're often not soluble in water, and even when they are, the solutions don't conduct electricity. The difference in these properties stem mostly from the differences in their polarities. So yeah, polarity is crazy important. So important that we'll be doing a whole episode on it soon. Until then, I want to thank you for the bond that you have to Crash Course Chemistry, whether it's casual observer, faithful viewer, or committed subscriber. Today, if you were paying attention, you learned that chemical bonds form in order to minimize the energy between two atoms or ions. You've also learned that the chemical bonds may be covalent if atoms share electrons, and that covalent bonds can...
All right. So, like I was saying, some might be over here. Some of that stuff like bond length, I'm not worried about, so you don't really have to know the length of the bonds or that equation. But that other stuff, give me something that you learned. Say that again? They minimize something, okay. Sure, yeah, all right. You gotta give me something so we can keep watching these. It tells me you're learning something. What's it?
There's something with the charges and some equation or something.
Yeah, absolutely. So like a positive charge and a negative charge will like attract. Will attract. What about different kinds of bonds? Can you name the three different bonds you talked about in the video? Those are,
Well, not really, but
somebody said something?
chemical bonds.
They are chemical bonds, yep, but there's three types
No.
of chemical bonds.
Ionic.
Ionic, boom, there's one.
Polar.
Polar, covalent, yep, polar covalent, non-polar covalent. So non-polar covalent is also the same as just covalent. So same thing, non-polar, covalent, and covalent are the same thing. So cool. So I'm not giving a handout to a note guide to go along with this. I would like you to try to take your own notes. Give it a couple days. If you would prefer, I did the same thing with the sophomores. If you'd prefer to have a note guide, I can give you one. But for now, let's try this out because for those of you who would like to go to college, this is a skill, a really important skill to acquire, note taking. Oh, and then also, before you leave, give me your exam back, the stuff I handed out. Or was one a assignment? No, both exams. All right, give them both back then. Is everybody good? Ready? Okay, we'll hang tight. You can take notes on a computer as well if you're good at that. Don't be messing around on it. Okay, let's start. Okay, so we're going to start with the electrostatic force. The electrostatic force is the idea that like particles repel each other and opposite particles attract. So what are we referring to when I say particles? Does anybody know? It has to do with charges too. What's a positive charge? What's the particle that has a positive charge? Proton. Yep. And then what's the other one? It's a negative. Electron. Yep. So 2 electrons don't want to be near each other, and 2 protons don't. Well, that gets hazy, but we don't need to worry about protons being close to each other. 2 electrons don't like getting close to each other. But an electron likes protons, and protons like electrons. So that's the electrostatic force. Chemical bonds are attractions between atoms. So, okay, I guess I wrote it on there. I was going to ask you a question. When one atom has more pull from their electrons than other. So we'll talk about that in a minute. Yeah. And then atomic stability. Atoms are happiest, air quotes, happiest when they have a full octet of electrons. An octet is a full shell of valence electrons. And so stick that in your back pocket. We're going to talk about it in a couple minutes. Also, off subject, if you have any questions about your exam and how I grade them, please ask me. I'd love to know. And another thing is, if you think something is right and I counted it wrong, come up to me. I love to give points back. I'll give you all the points. And if you think, and if that so happens where something is wrong and I forgot to grade it, I will not take away points. Right? So I want you to come up to me. So you'll never lose points by talking to me. And then covalent, polar covalent, and ionic. We talked about that. We'll talk about it more here in a little bit. We getting there? All right, and you can see this is the skill I recommend because professors don't like to wait. This is a long time from now for you guys, but learning how to figure out what's important and what's just extra is a good thing to know. But at your stage, write it all down, unless you don't think it's important. But I'd recommend it. I'll give you one more minute. Okay, moving on. Atomic charges in a general sense. So what I mean by that is, I'll talk about it in a second. So if you don't have periodic tables out, I'd recommend taking them out. It's something to look at. Or if you have good eyes, you can look over to that one. I don't have that good of eyes. So column 1, also known as what? What do we call the elements in column 1? Starts with well, yes, it's the S block, but alkali. The alkali metals, so column 1, tends to have a charge of 1, positive 1. Column 2, also known as, does anybody know? Alkali earth metals are known to have a charge of plus 2. Column 3, same thing, tends to have a charge of plus 3. And then so I'm going to skip that bottom one and then move on to the negative. Column 5 tends to have a charge of negative 3. So if I say an atom has a charge of negative 3, what does that mean? It has 3 more electrons than what? No, not quite. I mean, you're right, but not quite. So 3 more electrons than what? No. So a neutral element, or a neutral atom, has the same amount of what and what? Protons and electrons. So if there's no charge on it, they have the same amount of protons and electrons. So going back to my original question, if an element has a charge of negative 3, that means it has more electrons, 3 more electrons than what? Than it needs, yeah, I guess. Looking for one word that starts with a P. 3 more electrons than protons. So in column 5, they like to have 3 more electrons than they do have protons. Does that make sense? And we'll work more on that. Get used to that kind of stuff. Column 6 has a charge of -2. And then column 7 has a charge of -1, or likes to have a charge of -1. Okay, and there's 2 columns I did not talk about. What are those 2?
4 and 8.
4 and 8. So 4, it does both. It can go both ways. Or it can go kind of both ways. So like sometimes they have a positive, if you look at carbon on your periodic table, look at all of the different amounts of charges it could have. So that's why I didn't include column 4, because they can go both ways. They're not necessarily usually positive or negative. And then 8. Why would 8 not have?
Because it's full.
It's a full. It has a full octet. So when they have a full octet, they're fine with how they are. They don't need any more electrons or any less electrons. And then transition metals are usually positive, as a general rule. And if you look at your periodic table and that D block, which is the transition metals, the D block, you can see there's a bit of a pattern to it. So like the first, second, and third columns in the D block are like 3, 4, 5, and then it kind of switches up. So there's no general rule to that, but they're usually positive. All right, moving on. Oh, this one, yeah, this is fine. Ions occurs when an atom does not have the same number of protons and electrons. Give me an example of a charge on an ion. Any example. Nitrogen? You say nitrogen? Yeah. Nitrogen, absolutely. What would the most common ion be? We're just talking about it. What column is it in? It's in 5. So what's the charge on a 5 often? -3. So a common ion for nitrogen would be -3. Does everybody understand how I'm doing that? We'll do it on the board too. Draw it out. But it's using the charges. And then molecule. A group of atoms bonded together. So, anybody know a molecule just off the top of their head? Salt. Salt, yes. Do you know what the molecule is? Yep, sodium chloride and chlorine. Yeah, so that would be a molecule where there's 2 atoms together. Water. H2O. There's 2 hydrogen and an oxygen. Moving on. Electronegativity. It's the power of an atom in a molecule it's the power an atom in a molecule has to attract the shared pair of electrons towards itself. Ugh, that's confusing. No, it's not. We'll talk more about that, and we won't do a whole lot. We'll do right at the beginning. We'll do some stuff with that, but then it gets kind of complicated with electronegativity. But it is something important to know. It's the ability for those 2 elements, one's pulling on the electrons more than the other. And that's where our bonds come in, the electronegativity of the 2 atoms. So ionic is a what? Let's say ionic blank. What's the blank there? anybody? Everybody. Ionic bond, right? Ionic bond, it's a bond type of bond. It's when the difference in electronegativity in a molecule is greater than or equal to 2. Polar covalent, when the difference in electronegativity is less than 2, but greater than or equal to 1.5 or 1.5. And this doesn't mean anything right now, but we'll get there. Covalent, when the difference in electronegativity is less than 1.5. You guys getting there? Getting close? Okay. Thirty more seconds. All right, moving on. So this is a chart of electronegativity. I wish I had, oh, okay, I got a good idea. So fluorine is the most electronegative of all the elements. That means it wants electrons more than any other element on the board. And if you look way over at cesium, it's got the lowest. It does not want electrons that bad. So, doing easy math, what kind of bond would a cesium and fluorine have? So, looking back on our bond types. So, how you do that is you subtract the most, or the least from the most. So, you take the least amount, so 0.7, and you subtract it from 4. 3.3, which is so high, it's super high, it's going to be ionic. Does that make sense where those numbers come from? We'll do it one more time. So if it has a 4, and this one has 0.7, what's the difference between the two? It's 3.3, yeah. There we go. So, get rid of that stuff. Okay. So we have 4, and then we have 0.7. They're commas because this was made by someone in England. They use commas instead of decimal points, which I don't know why, it's weird. So we have 4. 4.0 minus, let's do it this way, the up and down. 4 minus 0.7. So 10, and then this is 3, right? And then 3. That's how we get this number. It's the difference. It's the amount of numbers between the two. You guys know what difference is? Okay. So that's how we find the electronegativity difference. And this is super high, meaning it's ionic, meaning that fluorine will take all of its electron, or not all of it. It will take that electron super quickly. It's fluorines. It's not cesiums anymore. Tracking? Yeah?
Do we need one of those charts?
That's why I said we're not going to do a whole lot. If on a quiz, I would give you those, just because your periodic tables don't have it. So. Oh. So here's a representation of what we're just talking about. So when two atoms are the same, the exact same elements, so chlorine and chlorine, how much of a difference do you think the electronegativities will be? 0, right? So if this, it's off the top of my head, I can't remember it. Well, I guess we can find out. Chlorine is 3, and it has another chlorine. So what happens when you subtract 3 from 3? 0. There is no electronegativity difference. So that means they're equally shared. They're sharing it completely the same. So it's right in the middle. Good? And then polar covalent. Talking about polar covalent. So what does polar covalent mean? Yep. So in between, or less than 2, but greater than or equal to 1.5. So again, if we look, we got 3, and then we got 2.1, which gives us 0.9. That's no good. So one of the two are off. Got to remember 0.9. Huh. Yeah, it wouldn't be the polar covalent. Good call. So the diagram's off. But let's say, let's find us a polar 2.8 and 0.7, right? That would give, oh, let's go 0.9. So sodium and bromine would give us what? Subtract 0.9 from 2.8. Gives us what? 1.9, which is less than 2. Yep. So it's polar covalent. So bromine and sodium would be on that chart. Make sense? Cool. And then we talked about a totally ionic bond where the electron is completely stolen from the sodium. So the chlorine is stealing from the sodium. It's ionic. Cool? Okay. So we're going to do something real quick. We're going to move from Bohr models to dot diagrams. It's going to be the same thing, but just a little different. So let's do, somebody want to do it? You want me to do it? A Bohr model of sodium. Where did I put that marker? Good catch. Okay, sodium. Let's do sodium real quick. Okay, what do I put down? 2. 2s2. 2p6. 3s1. Okay. Bohr model. We know and love it. Same thing. And then we can do the same for both of these. Okay. Following? Get rid of that.
Wait, so you still use the slide rule, but you just do
So we'll learn here in a second. But so now I just have one on the outside. What's the outside of the what's the outside electrons called? Valence electrons. So now when we're talking about bonds, we only care about the valence electrons. Right? And there's only one. So I'm going to change this number to E. Or you can do a dot. Doesn't matter. We'll work up to dots. But this is now an E instead of a 1. Okay? Let's do chlorine now. So 2, 2, 6. We all know how to do this, right? 2, 5? Okay, all right. Okay, so let's do the same thing. I'm just going to do it again, even though I know you guys all got it. Same thing. That's still a Bohr model. All right, and then I'm going to get rid of the inside ones because we don't care about them anymore. Chlorine. And now we have 7 because it's in column 7. So we know how many valence electrons it's going to have. It's in column 7. So I'm going to get rid of the numbers again. So let's do the 2 first. So we got rid of the 2, and we're going to make it here and here. Okay? And you'll understand why I'm putting them there in a second. Get rid of the 5. Same thing. So we're going to put one here. We're going to put one here. 2, 3, 4, 5. Yes, yes, it does. And I was just trying to think of how to articulate that. So thinking back to your electrostatic rule, do electrons want to be next to each other? No. No, electrons do not want to be next to each other. They want to be next to protons, but not other electrons. And so when we start, so there's orbitals. We're going to breeze by this. There's orbitals where there's spaces where they have to be. So they have to be, on valence, there's only 4 outside orbitals. And so sometimes they just have to be next to each other. They don't like it, but they have to be. And if they can, let's say if we're talking about sulfur, right? We're talking about sulfur, then we would get rid of one of these. So now there's 2 that aren't next to any of them. We wouldn't get rid of this one because now they're still all together. Does that make sense why I did that? And then if we went to phosphorus, we'd get rid of this one. Not one of these, but this one. And then carbon, that's not carbon, it's silicon. Silicon, we get rid of that, right? So now they're all alone. Okay, so going back, so E, 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 all the electrons are there. This likes electrons, right? It's very electronegative. If the farther up and the farther right you go, the more electronegative it will be. And this one is indifferent about electrons. It could give it away. It's fine. So what'll happen is, I can't move this entire picture. I wish I could. This will go here. So get rid of that. Pretend it's still a circle. This is still a circle. I just I can't move the picture. And now it's shared. Yep. And so thinking back to your octet rule, does this satisfy the octet rule? Yes. Okay. So we have an octet rule. It's happy. And what about sodium? So sodium's in the S block. How many electrons are in the S block? They have 1. But a full S block was how many? 2. So it has a full S block now. This has a full S and D block, or P block, excuse me, a full 8. This one now has a full S block. This makes sense to people. Okay, cool. So now this has a full set of electrons, and this one also has a full block at least. It can't get a full 8, but it can get a full block, and it's happy with that. I did a lot there. Are you guys okay with that? You want me to do one more? Okay. We got 5 minutes. I'll do this quickly then. Yes, so this is where the charges come in, right? So if fluorine, okay, so let's do fluorine. And is it okay if I skip the making the Bohr model step? Yeah. So we know how many valence electrons will fluorine have? 7. 1, 2, 3, 4, 5, 6, 7. It's got 7. And then let's do lithium. How many? 1. It wants a full set, and then fluorine wants its full set, and lithium wants to get rid of it because this wants it. This is the one that wants electrons more than any other atom. So this electron will go here and become an E. And then we'll do the same thing like that. Cool? Okay. That'll be it for today. Goodbye.